Hi everyone, welcome to week 6 of Introduction to Causal Inference. In this week we'll be talking about estimation. If you have any questions or comments that pop up in your head as we go through this lecture, then as usual, go ahead and drop those in the YouTube comments down below and I'll reply to those as soon as I can. We'll start with recalling the identification estimation flowchart, where we start with some causal estimand, some causal quantity of interest that we're interested in estimating, and then we identify that quantity by turning it into a statistical estimand. That's a quantity that doesn't have any potential outcomes or do operators in it. And this is what we've been focusing on for the last few weeks, with the exception of specific examples where we actually did estimate causal effects. Now in this week, we'll be focusing on the estimation portion of this flowchart. So that's where we take some statistical estimand and then turn it into an estimate, an actual number that we'll use to report our causal effect. We'll start with some preliminaries, the first of which is conditional average treatment effects. The conditional average treatment effect is just like the regular average treatment effect, but now we're conditioning on X here. And we denote this with tau X, where this is the value of X that we're conditioning big X to be equal to. And throughout this lecture, we're always going to be assuming unconfoundedness and positivity. So we have identification. Identification is out of the way, and in order to do that, we just make these assumptions. More specifically, we have that the average treatment effect, which we'll denote with tau, is equal to this usual statistical estimand on the right here, where W is a sufficient adjustment set. And tau X, the CATE, the conditional average treatment effect, is equal to the same thing, but where we're conditioning on X. So still having W as the thing that we're marginalizing over. But now W isn't the only thing that's conditioned on. So W is not the only thing in our adjustment set. We also have X in the adjustment set because we're conditioning on X here. And the X in conditional average treatment effects does not need to be all observed covariates, though it often is. People often be talking about X being all the covariates that they've observed so that their conditional average treatment effects are as individualized as possible. In the course book, we actually call those individualized average treatment effects, so that's a specific kind of conditional average treatment effect. With the preliminaries out of the way, we come to the lecture outline. In this lecture, we'll see a variety of different methods for estimation. We'll start with what I call conditional outcome modeling. This is the kind of estimation that we used in the examples that we saw in lecture 2 and lecture 4. So hopefully it'll look reasonably familiar. Then we'll move on to methods that will hopefully be a bit more data efficient than the conditional outcome modeling methods we'll see. Next, we'll see propensity scores and inverse probability weighting for estimation. And finally, I'll mention some other methods for estimation that are a bit outside the scope of an introduction to causal inference, but I'll give you a few details about them so you get an idea for what's kind of going on. And I have pointers to learn more about these in the course book. Great, so let's jump into conditional outcome modeling. Here is the adjustment formula for the average treatment effect that's hopefully reasonably familiar to you by now. So on the left-hand side, we have a causal estimand, and on the right-hand side, we have a statistical estimand. And we want to turn this statistical estimand into an actual estimate. We want an estimator that can take in data and then give us that estimate. So there's two things we'll need to do here. The first is to model these conditional expectations. Here we can use any statistical model that models this conditional expectation. So if you've used scikit-learn before, you can pretty much just take anything out of scikit-learn and plug it in to model this conditional expectation, assuming that it's minimizing the mean squared error of the true y's and the predicted y's given treatment and W. So you can even use fancy models like deep neural networks to model this conditional expectation. What I'm going to do now is rewrite this conditional expectation using mu. So I've just taken the thing on the top and rewritten it using mu to mean this conditional expectation. Now we get this estimator, where mu hat here is some model trained using mean squared error to predict outcome from treatment and W. And in order to approximate this expectation over W, we take a sum over all the data samples I, and then we use that I to index W here. And then because it's a mean, we normalize that sum. So we divide by 1 over n, where n is the number of samples. So that's how we get an estimate for the ATE using conditional outcome modeling. Here, mu is the conditional outcome model. And if you think back to the full examples where we included estimation in week 2 and week 4, we used a conditional outcome model estimator, or a COM estimator, where the specific model that we used was linear regression. Now, how might we extend this to estimation of conditional average treatment effects? Here is the average treatment effect COM estimator that we just saw. And here is the CATE estimand that we saw in the preliminary slide. On the rightmost side, we have the statistical estimand that we'll use to guide how we get an estimator here. Similar to the last slide, we'll define a mu. This mu is almost the same as the mu we used in the last slide, but now it also takes x as input and corresponds to an estimand that is conditioning on x. Now we can get a COM estimator for the CATE that looks just like the COM estimator for the ATE, except now x is also an input to this model mu hat here. So now when we train the statistical model, it also needs to take as input x. So the model that we train will train to predict y from treatment, W, and x. And additionally, this sum over I is only going to be for the samples where xi, so the sample where it's x equals this x here, that defines the conditional average treatment effect, the specific kind of conditional average treatment effect that we're looking at. And similarly, this n sub x here is the number of such samples in that sum. If there's only one sample like that, you could still use that as the estimator for that CATE. And you could even call it an estimator for the corresponding ITE, the individual treatment effect for that example. And the first question of this lecture is, what could go wrong with this estimator? COM estimation goes by many different names, and we're just going to list some of those names here so that you know what people are talking about when they say these things. The first is G computation estimators, where the G stands for generalized. This comes from the fact that when Jamie Robbins came up with these were for the generalization to time-varying treatment. So if you imagine a graph where you have many nodes for treatment over time, where each of the treatment nodes is a different time point for that treatment. Another name you might see for COM estimation is parametric G formula, where G again here stands for generalized, for the same reason as G computation. The relevant statistical estimand there was originally called G computation formula. And the motivation for this name is that G computation commonly gets confused with this completely different kind of estimation called G estimation. So maybe people won't confuse G formula with G estimation as much as they confuse G computation with G estimation. The next is standardization. And you might also hear COM estimators referred to as S-learners, where the S here stands for single because we fit a single model for mu. We'll soon see that you could imagine fitting more than a single model for mu. Now, imagine that we're using COM estimation in high dimensions. So the W vector here is high dimensional, and t is a scalar, only one-dimensional. And we're fitting a model mu hat to this data. So here I've depicted a neural network, but you could imagine any model for this. It's reasonable to think that the model could ignore t here, because t is only one dimension in the high dimensional vector of input to the model. So say w is 100 dimensional, then t is 1 out of 101 dimensions. The model might not need t to predict y well, given these 100 other dimensions. So in a neural network or a linear regression, this means assigning 0 to the weights that are coming out of t. Or it could even just be assigning really small values to those weights so that t isn't contributing much in the prediction for y. So this kind of intuition might lead you to believe that COM estimation can be biased towards 0. So the ATE estimates might be a bit on the small side in absolute value. And in this paper here, they found some evidence for that. So the problem, to recap, is that our models could ignore treatment, leading to estimates of the ATE or CATE that are biased towards 0. This leads us to the natural question: how can we ensure that the model doesn't ignore t? The solution that we'll consider is what we'll call grouped COM estimation, or GCOM estimation. At the top here, I've copied the COM estimator for the ATE, and the GCOM estimator will be very similar, but it won't use the same model for mu. Rather, we'll use mu1 as the model for all the treatment equals 1 data, and mu0 for all the treatment equals 0 data. So we have two models here, mu1 hat and mu0 hat, where each is fit to a different treatment group. So if we draw a neural network again, we have a single neural network for the COM estimator, and this single neural network takes both treatment and W as input to predict Y. In contrast, for GCOM estimation, we would have two neural networks. One neural network for the treatment equals 1 group. So all the data that has t equals 1 will be used to fit this t equals 1 network. And another network for the t equals 0 data. That whole group of data will be used to fit the t equals 0 network. And then we don't need to use t as input to these networks. They only need to take w as input. T is encoded into the fact that we're using two different networks. So while in regular COM estimation, the single model is fit with all of the data, while in GCOM estimation, the first model is fit with all the treatment group data and none of the control group data, and the second model is fit with all the control group data and none of the treatment group data. This leads us to the problem that these networks might have higher variance than they would if they were trained on all of the data, right? We might not be efficiently using our data. Now that we're at the end of this section, I'll leave you with the following question, which is: write down the general form of a COM estimator and a GCOM estimator. In the last section, we saw that COM estimation can be biased toward 0. This motivated us to move to GCOM estimation, which we saw that can be a bit inefficient with data. In this part of the lecture, we'll see some methods where we try to increase the data efficiency. The first is TARNet. So here's what the model for a COM estimator would look like. We're going to use neural networks again here. And this network takes both T and W as input. We saw that the problem with this was bias. It could be biased towards 0, which led us to GCOM estimation. Here we depict two neural networks, one for the treatment group data, one for the control group data, and both of these only take W as input. The problem with this is that we saw it could have too much variance because both of these networks are trained with less data. This motivates a sort of hybrid architecture that we have in TARNet, where we use all of the data to train this network. So we only give W as input, and then the network branches off into two heads, one for the treatment group and one for the control group. The hope is that this will kind of take the best of both worlds here in the COM estimation and GCOM estimation. And technically we can use this network architecture in a COM estimator. So this single network would be the mu hat in the COM estimator, where the input for T is used to know which head to branch off into after getting to the treatment agnostic representation in the middle here. However, what I said on the last slide was not completely true. So it is true that the subnetwork that maps from W to this treatment agnostic representation uses all of the data. It's not true that this whole network uses all of the data. So the head that branches off for the treatment group only uses the treatment group data. The subnetwork for that head is only trained using treatment group data. Similarly, the subnetwork for the T = 0 head is only trained using the control group data. We'll now move on to another method that tries to increase data efficiency, the X-learner. I don't really keep up with the X-Men movies, but I think there might be an X-learner X-Men movie coming out pretty soon. It's this X-Men that's just always reading books and is just really, their superpower is basically just reading books. Anyway, so there's 3 steps to the X-learner. The first step is to estimate mu1 hat and mu0 hat, where each of these models only take X as input. And for simplicity, we'll be considering the case that they consider in their paper, which is that X is a sufficient adjustment set and is all observed covariates. Okay, so we just pick any model from scikit-learn, say, and then fit it for mu1 hat, and do the same for mu0 hat. It can be a different model if you like. Then in step 2, so we're going to use the same numbering for the steps here that they use in the paper, but step 2 is kind of like 2 parts. So in step 2a, we impute the individual treatment effects. So for the treatment group data, we compute the ITEs for the treatment group using the observed outcome, which is Y1 for each of the individuals I. And then we use the model that we fit for mu0, where we feed in that individual's covariates to impute this treatment effect. So we're kind of imputing this potential outcome, the one that we don't observe due to the fundamental problem of causal inference. And then we do the analog in the control group. So here, for the control group ITEs, we observe the Y0 potential outcome as the observed outcome Y. And then we impute the potential outcome Y1 using the mu1 model that we fit in step 1 to impute this ITE for the control group as well. Okay, so for a given ITE, for say let's consider the treatment group ITEs, for a given treatment group ITE, we use the data from one outcome in the treatment group here, and we use all of the control group data. And the way we're able to use all of the data, not just one outcome in the treatment group, is doing what we do in step 2b. We fit a model tau1 hat of X to predict tau1 I, right here, this ITE that we just got in the last step, from Xi. Okay, so we feed in all of these tau1 I hats, and then we try to predict them from the corresponding covariates, Xi. So this model tau1 hat is going to use all of the data. So it already used all of the control group data here. And then now that we're using all of these imputed ITEs, where we use all of the treatment group outcomes, we're going to end up using all of the data in total. And tau1 hat will give us estimates for all of the different data points. X can be any X here, whereas in step 2a, we only got estimates for the treatment group data with tau1 I hat. Then we do the exact same thing with the tau0 I hat data that we add here. And that gives us another way to estimate the conditional average treatment effects, tau 0 hat of x. So we now have two different estimators of the conditional average treatment effect, tau 1 hat and tau 0 hat. In step 3, we combine these using a weighting function, g of x here, that can be anything that outputs numbers between 0 and 1. In the XLearner paper, they say that they find that using the propensity score works fairly well, which we'll see shortly. But you don't need to be using the propensity score. That concludes the second section of this lecture, and I'll leave you with this question. What would motivate someone to consider a more complex type of estimation, like the two that we just saw, than COM or GCOM estimation? In this part of the lecture, we will introduce propensity scores, and then we'll use those to introduce the method of inverse probability weighting for estimating causal effects. The propensity score is just the probability of taking treatment equals 1, given the relevant covariates W that we'd be adjusting for. So this quantity describes your propensity for taking treatment, how likely you are to take treatment given W. And we'll use E of W to denote the propensity score. So here's the kind of amazing thing about propensity scores. Given positivity, if you have unconfoundedness, given W, so if W is a sufficient adjustment set, then you have unconfoundedness given the propensity score, E of W. This is kind of amazing because even if W is super high dimensional, the propensity score is only one dimensional. Right? It's only a scalar. It's just the probability that treatment equals 1 given W. And this really cool result is known as the propensity score theorem. Mathematically, we can write it as follows. To see why this is true, I'll give you a graphical proof. So consider that this is the graph, that W is a confounder of the effect of T on Y, and importantly here, W is a sufficient adjustment set. This edge from W to T is the causal mechanism that we can write as just this conditional distribution, P of T given W. Now, if T is binary, this isn't key to the argument, but if T is binary, we can completely describe this conditional distribution of T using just the probability of T equals 1 given W, right? So to get the rest of the distribution, which is the probability that T equals 0 given W, you just subtract this from 1. So this quantity completely describes that distribution. And this is just the propensity score. Okay, so let's just put that propensity score there in the graph. So now we have a node in the graph for the propensity score. And what this theorem is saying is that if W blocks all backdoor paths from T to Y, then that implies that E of W, the propensity score, blocks all backdoor paths from T to Y, which should hopefully be graphically clear now. If you want to see a non-graphical proof using just equations, then go ahead and check out Appendix A.2 of the course book. So the propensity score has pretty big implications for the positivity unconfoundedness trade-off that we saw back in week 2. So for this trade-off, recall that the overlap decreases with the dimensionality of the adjustment set. Another way of saying that is that we get more likely to have positivity violations, or existing positivity violations get worse. So here's a super high dimensional W. Because W is so high dimensional, it seems likely that we'll have positivity violation. But the propensity score theorem tells us that we don't need to condition on W. We can just condition on the propensity score, which is a scalar. So the propensity score is a bit magical in that it takes this high dimensional W and reduces it to just a single dimension. Now, if we condition on just this scalar, we're much less likely to have overlap violations because it's only one-dimensional. Great, so problem solved, right? Unfortunately, not really, because we don't have access to the propensity score. The best we can do is model the propensity score using some model, say in scikit-learn. For example, logistic regression is really popular. And when we model the propensity score, we're just shifting the high dimensionality problem to the modeling of the propensity score. So unfortunately, we haven't really solved this positivity unconfoundedness trade-off. All right, so I now have 3 questions for you about what we just saw on propensity scores. The first is, what is the intuition behind why we can condition on the propensity score E of W instead of W? The second question is, what is attractive about conditioning on E of W as opposed to W? And the third question is, why does this not solve our positivity issues when W is high dimensional? Now that we've defined propensity scores, we'll be moving on to inverse probability weighting, and for that we'll first introduce pseudo-populations. The general idea here is that even though association is not causation in the general population because of confounding, we'll create pseudo-populations where association is causation. So consider a regular population where W is a confounder of the effect of T on Y. One way to see why association is not causation is that we have a backdoor path from T to W to Y because we have this edge W to T. And we have this edge W to T because the conditional distribution of T given W is not just equal to P of T, right? So T actually depends on W. We need to keep W behind the conditioning bar here. Well, what if we could reweight this population so that we end up with that distribution equal to just this marginal, just P of T, or even just due to some constant. Importantly, it just doesn't have W behind the conditioning bar here. Then in this pseudo population, really the graph looks like this, right? So T no longer depends on W. And we can get to a pseudo population by this via reweighting. More specifically, we reweight by the reciprocal of the propensity score, by the inverse probability of treatment. And the intuition for this reweighting is that we take this conditional distribution, P of T given W, and we just reweight it. So we reweight all of the examples by the inverse probability of treatment, and then those two cancel and we end up getting 1. Importantly, the thing that we end up getting does not depend on W. So by multiplying by the reciprocal of the propensity score, we've basically deleted this edge from W to T. Okay, now we can introduce inverse probability weighting. We start with some observational distribution that's, say, generated by this causal graph. Importantly, we need that W is a sufficient adjustment set. So from this observational distribution, we get observational values of the outcome, Y. And then we're going to reweight these by the reciprocal of the propensity score, the inverse probability. And as we gave some intuition for in the previous slide, you can think of this reweighting as deleting this edge from W to T. Then all that's left is to specify that the causal estimand that we're interested in here is the expected potential outcome YT, and then we're going to limit the specific data samples that we look at to the ones that have treatment T equals little t, so the little t's match here, and then we take an expectation of this whole thing. So on the left-hand side here, we have a causal estimand, and then we have a corresponding statistical estimand on the right-hand side that we get from inverse probability weighting. And you can see the proof for this in Appendix A3 of the course book. It turns out that this statistical estimand is equivalent to the estimand that we're used to seeing, the one in COM estimation. But this formulation of the statistical estimand suggests a different kind of estimation, inverse probability weighting. So we'll now write down the ATE, so just taking the above equation and plugging in t equals 1 and t equals 0. And we're now going to use propensity score notation. So here we have 1 minus the propensity score, because remember, propensity score is probability of t equals 1, not probability of p equals 0. Then we can turn this statistical estimand into an estimator using what you might expect. We model the propensity score using E hat here, and then we approximate this expectation where we're only pulling out the treatment equals 1 data using this sum and dividing by 1 over the number of treatment samples. Similarly, we do the same for this expectation when we're selecting out the t equals 0 samples. Okay, so that's our basic IPW estimator. This then leads me to 2 questions. The first is, what happens if the estimated propensity score for some unit is either 1 or 0? Similarly, what happens if the estimated propensity score isn't quite 1 or 0, but it's near 1 or 0? So we just saw IPW estimation of the average treatment effect, the ATE, but what about IPW estimation of the conditional average treatment effect? CATE estimation is not quite as natural with IPW as with COM, so it's beyond the scope of the course. A very simple extension would be to just restrict, so for the CATE for this X would be to just restrict this sum to data points where we have that specific X and then divide by the number of data points that have that specific X. And that's going to impact what terms are in this sum here. But this might not work super well, especially if not very many data points have that specific value of X. To read more about IPW CATE estimation, you can check out this paper and some of the references in it. Here are 2 questions for the propensity scores and IPW section. The first is, what is the graphical intuition for how inverse probability weighting deals with confounding? And the second question is, what do we model in IPW? And compare that to what do we model in COM/GCOM estimation. Alright, so we now have come to the last section of this lecture. There are many different methods for estimating causal effects, and many of these fall outside the scope of an introduction to causal inference. In this section, I'll give you a little bit of information about some of the other methods, and you can find pointers to more information about them in the course book. The first is that we saw modeling of the outcome mu in COM estimation, and we saw modeling of the propensity score in IPW estimation, but neither COM estimation nor IPW estimation modeled both of these. But of course there are estimators that model both the conditional outcome model and the propensity score and then use that for estimation. So to see a natural example of such an estimator that uses both of these, first consider COM estimation. And then from the propensity score theorem, we know that conditioning on W is just as good as conditioning on the propensity score. So we can get an estimator that uses both the conditional outcome model and the propensity score model by just plugging in the propensity score for W here. One special class of methods that models both the conditional outcome model and the propensity score model is known as doubly robust methods. One important property of doubly robust methods is that they are consistent if either the conditional outcome model or the propensity score model is consistent. And you can think of consistent here as meaning that given infinite data, our model will be correct. So given infinite data, mu hat will match mu and E hat will match E. Another property of doubly robust methods that is really cool is that they will theoretically converge to the estimand at a faster rate than COM or IPW estimation. You might interpret this as that doubly robust methods are more efficient with data, but these theoretical results are usually in the asymptotic regime where we have infinite data. So really for finite samples, it's a bit unclear. You can check out section 7.7 of the course book for references to relevant papers. The next other popular method is known as matching. In matching, we take individuals in the treatment group and match them to similar individuals in the control group, where they're similar in the sense that they have roughly the same covariates, at least the covariates that we need to adjust for. So here, this blue dot can match to this red one, and same with these other three. And then these three treated individuals don't get matched to anyone. So the ones that are not matched, same in the control group, there's many more individuals who are not matched in the control group. The individuals that are not matched are just thrown out of the analysis. And then we only consider the ones that are matched. This is because we need to find a close enough match in order to say that we've adjusted properly. So if we can't find a close match, then we just got to throw it out. And there's a large literature on matching. So for example, we can do this matching in the raw covariate space, we can do it in the coarsened version of the covariate space, or we can even do it in propensity score space. Each of those is a different kind of matching. And there's different criteria for what means close enough. So each of these ones with lines between them were deemed close enough. That's why they were matched. And then this blue was not deemed close enough to this red, for example. So that's why those two were not matched. Another popular method is double machine learning, right? So machine learning is really cool, but then if you have double machine learning, it's maybe twice as cool. And the name might have something to do with the fact that there's two stages to double machine learning. So in the first stage, we do two things. The first, we fit a model to predict y from w to get the predicted y hat. We also fit a model to predict t from w to get the predicted t hat. And that's stage one. Then in stage two, we use this y hat and this t hat. So using those, we can partial out w by fitting a model to predict y minus y hat from t minus t hat. So the idea here is that by subtracting these values that were fitted to w, so that's the y hat, and then t hat was fitted to w, by subtracting those out, it's like we're subtracting out w. We're partialing out w, and that is how we remove the confounding that w introduces into the observational data. And this is double machine learning in the sense that we use machine learning a first time in stage one, and then on top of the models that we get from stage one, that's y hat and t hat, then we fit another machine learning model on top of those to predict these residuals. And the last other methods that we'll consider are causal trees and causal forests. So you can think of causal trees as an extension of decision trees to estimate causal effects. And here's just an example of a decision tree. It's just like a flow chart. And then a forest is just a bunch of trees together. Decision trees and forests are flexible, but then more importantly, they yield valid confidence intervals. So everything we've seen so far, we estimate a point estimate for the ATE or for the CATE. But there's some uncertainty there because we only have finite data. You could imagine putting intervals around that point to convey that if we had gotten a different sampling of the data, the points might fall somewhere else, and it could be that they mostly fall in that interval. And this interval is supposed to encompass sampling variability. It's not supposed to encompass things like what would happen if we had unobserved confounding, which is what we'll see next week. And we're lucky enough to have Susan Athey, one of the researchers who developed these methods, give a guest talk in this course on causal trees and causal forests. And that will be the next talk in the course. If you want to get notifications for that talk or any upcoming lectures, then go ahead and subscribe below and hit the bell icon next to it. And with that, we'll conclude this lecture. See you in the next one.